Okay, hello and welcome everybody for the second series of 3 talks given by Akashdeep. Over to you.
Okay, thank you very much. Yeah, so last time I briefly. Sure. Yeah, so last time I briefly described the Almgren-Pitts min-max theory, and yeah, so I will recall some of the definitions from last time. So Mn plus 1 will denote a closed Riemannian manifold, and we'll assume that the ambient dimension n plus 1 is between 3 and 7. And we considered the area functional, which is defined on the space of closed hypersurfaces in M. So for a hypersurface sigma inside M, by area of sigma, we just mean the codimension 1 volume of sigma. And minimal hypersurfaces are precisely the critical points of the area function. Okay, so the idea of the Almgren-Pitts min-max theory is to construct closed minimal hypersurfaces using a min-max method on an infinite dimensional space. So in this theory, we work with the following spaces. Cm denotes the space of Cauchy sets in M. And informally speaking, this is the space of all regions U subset of M such that boundary U is n-rectifiable and area of boundary U is finite. We also need to work with space Zn M comma Z mod 2. So this is okay, so the space Zn M comma Z mod 2 is the space of mod 2 hypercycles in M. And informally speaking, this is the space of hypersurfaces. Sorry, so the space of closed, unoriented, hypersurfaces sigma in M such that sigma is the boundary of a region U. So here U is in CM. So we have naturally defined topologies on these two spaces, and those topologies are given by metrics. So the flat metric on the space CM is defined as follows. So the flat distance between two regions, omega 1 and omega 2, is just the volume of the symmetric difference of omega 1 and omega 2. We also have flat metric on the space Zn. And this roughly means the following. Two hypersurfaces sigma 1 and sigma 2 are closed in the flat metric if and only if sigma 1 minus sigma 2 is the boundary of a region omega such that volume of omega is small. So we have the boundary map from the space CM to the space of hypersurfaces Zn. This just sends the region U to the boundary of U. And this map is 2 to 1 because if sigma is the boundary of a region U, then sigma is also boundary of M minus U, and these are the only two possibilities. We have the following theorem. So theorem by Marques and Neves. The space CM with the flat topology is contractible. And the boundary map is a double cover. Therefore, this space Zn, which is the space of hypersurfaces, is homotopy equivalent to Rp infinity. And the cohomology ring of this space with Z mod 2 coefficients is the polynomial ring over Z mod 2. So here lambda is in H1 Zn comma Z mod 2. Okay, so in addition to these two spaces CM and Zn, we also need the space of n varifolds. So we'll use this notation V and M to denote the space of n varifolds in M. And I'm going to define this notion of varifolds and say a few more things about the varifolds. So let G and M be the Grassmannian bundle of unoriented n-dimensional hyperplanes over M. then an n varifold is just a positive radon measure on this Grassmannian bundle. And we use this notation V and M to denote the space of all n varifolds in M. We endow this space Vn with Wickstad topology. This means the following. If we have a net Vi, I in some index set capital I. So a net of varifolds Vi converges to a varifold V in the Wickstad topology if and only if integral over G and M H Y omega integrated with respect to the radon measure Vi converges to integral over G and M H Y omega dV Y omega for all H in C0 GNM. So here I'm using the following notation. This Y is a point in M, and omega is an n-dimensional hyperplane in the tangent space of M at Y. And H is a continuous function on the Grassmannian, so H Y comma omega, and integrated with respect to the radon measure Vi. This converges to integral of H with respect to the radon measure V. And this is precisely the meaning of the Wickstad topology. So we can give an example of some kind of canonical example of varifolds. So let sigma in N, sigma in M be a C1 hypersurface. Then sigma defines an n varifold as follows. So use this notation to denote the varifold defined by sigma. So this acting on H. So H is as before a continuous function on the Grassmannian is equal to integral over sigma H evaluated at x comma tangent space of sigma at x integrated with respect to the n-dimensional Hausdorff measure on sigma. Now by this formula, we define the n varifold associated with sigma, but this formula makes sense if sigma is just n rectifiable instead of C1. Because in that case, we can define the tangent space Tx sigma in a measure theoretic sense for Hn almost every x in sigma. So more generally, so instead of C1 hypersurfaces, more generally, we can consider n rectifiable sets sigma, and given an n rectifiable set sigma, we can define a varifold associated to sigma in this way. Okay, so Yeah, so. Okay, so this was an example. So I will talk few more things about the varifolds. So let P from G and M to M be the canonical projection map. Given an n varifold V, we use this notation norm V to denote the push forward of the radon measure V by this projection map P. So V is a radon measure on the Grassmannian, and if we push it forward by P, we get a radon measure on M. And this means that this notation means that norm V, the mass of V on a set A is V of P inverse A, where A is a subset of M. So next, let us consider phi to be a map, to be a C1 map from M to M. And V and N varifold. Then we can define the push forward of V by this map phi as follows. So phi push forward V acting on a continuous function H is equal to integral over. So I'll explain this. H phi y comma d phi. So this is the derivative of phi at y acting on omega multiplied by the Jacobian factor j phi at y comma omega dv. So here j phi y comma omega is the Jacobian factor. It is defined as follows. We consider the derivative of phi at y and restrict it to the n-dimensional hyperplane omega. And we take its transpose. Okay, so this comes in the change of variable formula. Now we take the determinant of this. Take the square root. And this Gn plus M is the set of all y comma omega in the Grassmannian such that the Jacobian factor is positive. Okay, so this is the definition for push forward of a varifold for an arbitrary varifold and an arbitrary C1 map. But if we restrict ourselves to the case when V is a varifold defined by a hypersurface and phi is a diffeomorphism, a C1 diffeomorphism, then using the change of variable formula, this just means that phi push forward, the varifold defined by sigma is just the varifold defined by phi of sigma. So now we can talk about the first variation of varifold because we have this push forward map. First variation of a varifold along a vector field. So let X be a vector field on M and fxt be the flow of X. Then the first variation of V is an N varifold. Then the first variation of V along X is defined as follows. We take ddt at 0, the mass of fxt push forward V. So we consider the total mass in M. And we recall that this is just equal to ddt at 0 area of fxp sigma if V is the varifold defined by a hypersurface sigma. So this is the first variation of a hypersurface, and we use this expression to define minimal hypersurfaces. So this is the first variation of a varifold along a vector field X. And if we do some computation, this will be equal to integral over the Grassmannian divergence with respect to omega of X of the vector field X at small x. And the integral is with respect to dV. So here, this notation means the following. So capital X is a vector field, small x is a point in M, and omega is an n-dimensional hyperplane in the tangent space at X. And this is equal to summation inner product nabla EI xi comma EI I from 1 to n, where EI is an orthonormal basis for this hyperplane omega. Yeah. No. So for instance, we can have union of two planes. So there is a large singular set. Yeah. So yeah, so we say that V is a stationary varifold if the first variation of V along X is 0 for all X, for all vector field X. So we recall that if V is the varifold defined by hypersurface sigma, then V is stationary if and only if sigma is minimal. Okay, so in the first variation formula, we see that the integrand is divergence of X with respect to omega, and this function X comma omega going to divergence of X with respect to omega at X. This is a continuous map. It's a continuous function from the Grassmannian to R. Therefore, by the definition of the Wickstead topology, the first variation is continuous with respect to the varifold topology. Yeah, so the first variation is continuous with respect to the varifold topology. So in particular, if we have a sequence of varifolds Vi converging to V as varifold, then and each Vi is stationary, then V is also stationary. So limit of stationary varifolds is again a stationary varifold. Yeah, so that's all I wanted to say about varifolds. Now, now we go back to the Almgren-Pitts min-max theory. So we recall from last time that we fixed some finite simplicial complex X. And we considered phi to be a homotopy class, which is a homotopy class of continuous maps from X to the space of hypersurfaces Zn. This is an infinite dimensional space, and on this space we do the min-max. So in particular, we consider the following min-max quantity corresponding to the homotopy class pi. So we denote it by L pi, and this is equal to area of phi x, small x is in capital X, and then we take in overall pi in pi. So phi is a map from X to Zn. So for each small x, phi x is a hypersurface. We are taking the area of that hypersurface and considering this min-max quantity. So a sequence of maps phi I inside pi is called a minimizing sequence. If limit I tends to infinity, sup of area phi ix, small x is in capital X. This limit is equal to this min-max number L pi. So this is the definition of a minimizing sequence, and given a minimizing sequence, phi I in pi, we use the notation C phi I. This is called the critical set of this minimizing sequence phi to denote the set of all n varifolds V such that the total mass of V on M is this min-max number L pi, and there exists a subsequence Ij and a sequence of points xi in X such that we consider these hypersurfaces phi ij xj And then consider the varifolds defined by these hypersurfaces. These varifolds convert to V in the sense of varifolds. So Almgren-Pitts min-max theory says the following. So let us fix a finite simplicial complex X and a homotopy class phi. Then given any minimizing sequence phi I in phi, there exists a stationary varifold V in the critical set of phi I. So V is in the critical set of phi I means that the total mass of V on M is equal to that min max width, such that V has the following regularity. So V is equal to summation mi times the varifold defined by sigma I is from 1 to some q, where mi's are positive integers and sigma I is a collection of disjoint closed minimal hypersurfaces. So very roughly speaking, the idea of the Almgren-Pitts min-max theory is to first show that given any minimizing sequence, we can find a stationary varifold in the critical set of that minimizing sequence. And from this definition, stationary varifolds is a generalization of minimal hypersurfaces. So they are critical points of the area functional in a weak sense. And then one needs to prove the regularity of this stationary varifold. So this V is indeed given by minimal hypersurfaces, and these minimal hypersurfaces have the following regularity. So I write it as a remark. So this, okay, so these sigma i's we can think of as different connected components of one single minimal hypersurface, which is the disjoint union of all the sigma i's. And since V is this integer linear combination of the sigma i's, the mass of V is sum of mi times area of sigma I. So this theorem tells us that the width is realized by the area of a minimal hypersurface, but different connected components of the minimal hypersurface can come with different integer multiplicities. Okay, so we have the following remark regarding the regularity of the sigma i's. Sigma I is smooth and embedded outside a singular set of Hausdorff dimension at most n-7. In particular, if if the ambient dimension n+1 is between 3 and 7, which I assumed at the beginning, then the sigma I, all the sigma i's are smooth and embedded. This is remark 1. And another remark is the following. Okay, so in the Almgren-Pitts min-max theory, we considered maps from a finite simplicial complex to the space Zn. So in particular, we did the min-max on this space Zn to construct critical points of the area functional, but at the end, the critical point which we construct is not in the space Zn, but in the space Vn. So this V is obtained from these hypersurfaces phi I, j, x, j. So these hypersurfaces are elements in Zn, but to obtain V, we need to take limit as variables. So the reason we need the notion of variables in this Almgren-Pitts min-max theory is the following. So we need the notion of variable since the area functional. So we had this area functional defined on the space of closed hypersurfaces, but this area functional is not continuous with respect to the flat topology, the flat metric on the space Zn. However, this is continuous with respect to the variable topology. So what I mean by that is, if we have a sequence of variables Vi converging to V, this convergence is as variables, then the total mass of Vi converges to the total mass of V. So we can give an example to illustrate this. So let T be this line segment in R2. And we consider a sequence of rectangles let's say Ri is this rectangle with its interior, and height is 1 over I, and Ti is the boundary of this rectangle Ri. So Ti is boundary of Ri. Ti and T are in Z1 R2 Z mod 2. So now the area of this rectangle Ri is length of T times 1 over I, and therefore it converges to 0 as I tends to infinity. Therefore, by the so this Ti is bound this region Ri, and the area of Ri goes to 0. Therefore, by the definition of flat metric, Ti converges to 0 in the flat metric. However, we note that the length of Ti is 2 times the length of t plus 2 over r. So this shows that the length is not continuous with respect to the flat metric. However, if we take the varifold defined by this ti, then this converges to 2 times the varifold defined by t. So this as varifolds. So for this reason, here we take limit as varifolds, and when we take limits as varifolds, we can get some multiplicity. So this is precisely the reason why we get multiplicities here. Here also we have the multiplicity 2 when we take limits as varifolds.
This procedure now the variable operation is
So the proof does not work in this way. So we cannot say that all the elements in this minimizing in the critical set is regular. There exists one. So, yeah. Okay, so now I'll start talking about. I'm going to state the main results about the Morse theory for these minimal hypersurfaces. Okay, so let us recall that we have this area functional defined on the space of
there might be some free variable b that is not ready. You think there is exactly this one. You know that there's one that's regular. And there's some regular and some non-regular.
Yeah, I don't know an example, but the way the proof works showing that there exists one, but yeah, I don't think there is any concrete example about that. Okay, so we have this area functional on the space of closed hypersurfaces in the Riemannian manifold M, G. So the area functional depends on the Riemannian metric G. So let us write like this. Let us write it like this. Okay, so formally speaking, this area functional with respect to the metric G is Morse if every closed minimal hypersurface in M, G is a non-degenerate critical point of the area functional. So here non-degenerate means the following. So let sigma be a minimal hypersurface. And fxt be the flow of a vector field x. Then if we consider ddt at 0, area of fxt sigma, and this is going to be 0 because sigma is minimal. So we consider the second derivative. And if we do some computation, this is equal to minus integral over sigma phi times L sigma acting on phi. Here phi is the inner product x comma nu. So nu is a normal vector field locally defined on sigma. And this L sigma is an elliptic operator on sigma. So L sigma f is Laplacian f plus norm a sigma square. So this is the second fundamental form of sigma plus Ricci nu comma nu. So this is the Ricci curvature of the ambient Riemannian manifold times f square. So this is L sigma, and from this expression we can interpret this expression by saying that minus L sigma is a Hessian of the area functional at sigma. So yeah, so we say that sigma is a non-degenerate critical point if the kernel of L sigma is just 0. So we say that sigma is non-degenerate if kernel of L sigma is 0, and the Morse index of sigma is the number of negative eigenvalues of minus L sigma. And this is going to be finite because sigma is closed and L sigma is an elliptic operator. Okay, so we have the following theorem. So this is the definition for non-degenerate minimal hypersurfaces. We have the following theorem by White. For a generic metric, so I'll explain this term generic here. So generic is in the sense of bare categories. For a generic metric G on M, the area function with respect to G is Morse. This means that all the closed immersed minimal hypersurfaces in M comma G are non-degenerate, and such a metric is called a bumpy metric. Okay, so here generic means the following. Let M be the space of all C infinity Riemannian metrics on M. This is a complete metric space. Then if we denote by S the set of all G such that G is bumpy, then generic means that this set S contains a countable intersection of open dense sets of M, open dense subsets of M. So UI subset of M, open and dense. Okay, so yeah, so for For the bumpy matrix, that is when the area function is Morse, we have the following three theorems regarding the Morse index and multiplicities of the min max minimal hypersurface. Okay, so before I state those theorems, I need to introduce another definition. So you recall that the cohomology ring of the space Zn with Z mod 2 coefficients is the polynomial ring Z mod 2 lambda, where lambda is in H1, a map phi from a simplicial complex X to Zn is called a K sweep out if phi pullback lambda to the power K is non-zero in HK X comma Z mod 2. So phi is a K sweep out if it detects the kth cohomology class. And we define omega k to be the min max number corresponding to the kth cohomology class lambda to the power K. Omega k m comma g is so area of phi x. Small x is in the domain of phi. And then we take inf over all phi such that phi is a K sweep out. So omega k is the min max number corresponding to the cohomology class lambda to the power K. Okay, so with this definition, I can state the main theorems. Let G be a bumpy metric. Theorem 1 by Marques and Neves. So okay, so as in the setup of the Almgren-Pitts min-max theory, let pi be a homotopy class of maps from some simplicial complex X to Zn. Let phi I in pi be a minimizing sequence. Then there exists stationary varifold V in the critical set of phi I such that phi is summation mi times, so V is summation mi times the varifold defined by sigma I. So this mi is same as in this theorem. Mi's are positive integers and the sigma i's form a collection of disjoint closed minimal hypersurfaces. So we have this and the following Morse index estimate. So summation index sigma I is from 1 to q is less than or equal to the dimension of the parameter space X. So the sigma is were different connected components of the minimal hypersurface, which we obtained by the Almgren-Pitts min-max theory. And this says that the index of that minimal hypersurface is bounded from above by the dimension of the parameter space X. So this is theorem 1. This gives the index upper bound for the min-max minimal hypersurfaces. theorem 2 by Zhou. So pi as above, as before. There exists a minimizing sequence pi I in pi such that there exists a stationary variable V in the critical set of phi I such that V is equal to summation the variables defined by sigma I is from 1 to q. So the sigma is are same as in this theorem. This is a collection of disjoint closed minimal hypersurfaces. So here we don't have any mi. So this says that all these multiplicities all the multiplicities mi's are equal to 1. So this is equal to 1 for all I. So V is summation sum of the variables defined by sigma i's, and each sigma I is two-sided. So a hypersurface sigma is called two-sided if the normal bundle is trivial. So in this theorem, some of the sigma i's can be one-sided, but this theorem of Zhou says that each sigma I is two-sided. Okay, so these two theorems, theorem 1 and theorem 2, are about homotopy min-max. Theorem 3 is going to be about the cohomology min-max, that is about this min-max. Theorem 3 by Marques and Neves. So let k be a positive integer, then omega k, which is the min-max number corresponding to the cohomology plus lambda to the power k, is equal to the min-max number of some homotopy plus phi k. So omega k is the min-max number corresponding to some homotopy class, and I said that theorem 1 and theorem 2 holds for homotopy min-max. Therefore, they also hold for cohomology min-max because of this equality. Okay, so we have theorem 1 and 2 for cohomology min-max. Moreover, we have index lower bound for the cohomology min-max. So there exists a smooth closed two-sided embedded minimal hypersurface sigma k such that omega k is area of sigma k. So this is the multiplicity 1 for the cohomology min-max, and index of sigma k is equal to k. So theorem 1 already implies that there exists sigma k such that index of sigma k is less than or equal to k. So theorem 3 actually proves the lower bound for the cohomology min-max. Okay, so I guess the time is almost over. I'll just make a remark and okay, so these are the three theorems which summarize the Morse theory for the area function. So I'll just make a remark about the higher dimensional extensions of these three theorems. So we said at the beginning that G is a bumpy metric, that is the area function with respect to G is Morse. But for theorem 1, it is not necessary to assume that G is bumpy. So theorem 1 holds, the Morse index upper bound holds for any metric, but for theorem 2 and 3, we do need the assumption that G is bumpy. Okay, so theorem 1 has been extended in higher dimensions. That is when the ambient dimension n+1 is greater than or equal to 8 by Lee. And finally, theorem 2 and theorem 3 have been extended in the case when the ambient dimension n+1 is equal to 8 by Lee and Wang. Okay, so I'll stop here.
Questions for Akashdeep from the live audience or?
So index has no, so index was defined in terms of the index of that L sigma, the Jacobi operator.
Yeah.
So the definition makes sense for any, even if the area function is not Morse. Yeah, so Morse just says that its kernel is 0. Mhm.
So, the concept for a generator chosen dividing sequence.
Mhm.
So, the Almgren-Pitts theory says that you have some stationary. But so, for example, particular stationary
Yeah, for a generic metric, there exists a unique element in the critical set, which is regular. But yeah, it is possible that it contains many such things in the critical set. Yeah. Yeah, so I can draw a picture in the finite dimensional case. So let us consider torus embedded in R3. And we have this height function on this torus. And this is a index 1 critical point of H. So near this critical point, the torus looks like this. So this is the critical point. So we can detect this critical point by one parameter min max. So we consider homotopy class of these curves. Now, okay, so the soup for H for this curve is attained at these points. So we can take such a sequence. Maybe we take this curve and so on. And here, in fact, we have a curve for which the soup is exactly equal to this. But in the infinite dimensional case, we may not have this picture. What we can have is that sequence of curves such that the max of that function along that curve is approaching to this critical point. And then we show that the limit is going to be a stationary varifold. I mean, so it is a critical point of the area functional in a weak sense.
All negative, stationary backwards are rectifiable.
Yeah, they will all be rectified, but yes. Let me think here. No, actually, that may not be the case. Again, the way the proof is done is that first it is proved that they're almost minimizing. So in a sense, they're not quite minimizing, but they are almost minimizing, meaning if we want to decrease the area of that variable, we have to, if we consider a one parameter deformation, which at the end decreases the area by a certain amount, it must go up by a certain amount. So you show that there must exist at least one almost minimizing variable, and then we prove the regularity. So the first step in the proof of regularity that it is rectifiable. So again, the proof says that there exists at least one which is rectifiable. So this, so I wrote V as a limit of phi j xj. So these variables are rectifiable, but limit of rectifiable need not be rectifiable. So that is the difficulty, I think. Yeah.
There are no further questions. Let's thank Akashdeep.
Thank you.